Hello everyone, welcome to a new lecture in the series of data-driven model predictive control. In this lecture, we will be briefly reviewing some approaches in system identification and we will mostly focus on the Ho-Kalman-Kung algorithm, which is a linear state space identification approach. Here is the overview. We will be starting with a brief introduction to linear state space identification. Then we move on to the Ho-Kalman-Kung algorithm, which is followed by a numerical example. As the name indicates, linear state space identification deals with identification of linear state space models using available data, which is in the form of input and output data and also called as training data. Let's recall the linear state space model from the previous lecture, which can be represented as in equation number 1. Here, the model parameters are the system matrix A, the input matrix B, and the output matrix C, which are considered to be unknown in the case of system identification problems. The available information consists of the input and output samples or observations, which can be stored as columns of a data matrix, results in the input data matrix capital UD and output data matrix capital YD. Here, capital D stands for the number of data samples. Then, the linear state space identification problem is to estimate the model parameters or ABC matrices using the input-output data. In the past, many approaches for linear state space identification were proposed in the literature, which can be broadly grouped into realization methods and prediction error methods. Realization methods are mostly based on linear algebra techniques, which uses linear transformations, projections, factorization such as singular value decomposition, etc. Whereas the prediction error methods or PEMs can be considered as optimization based identification methods in which the model parameters are computed by optimizing a loss function, which is normally a function of the prediction error. In this lecture, we will be mostly focusing on realization based approaches. Next, we move on to the Ho-Kalman-Kung algorithm, which is one of the initial approaches in the linear state space identification, and it is a realization based method. Initially, this approach was proposed by Ho and Kalman and was known as Ho-Kalman algorithm, and it uses the Hankel matrix constructed with the impulse response data for identifying the model parameters. In general, a Hankel matrix has constant entries in each ascending skew diagonal. And in this lecture series, the Hankel matrix is denoted by bold letter H as in equation number 3. Here, the Hankel matrix consists of capital N by capital H samples of the vector V starting from the time instant k. So where capital N denotes the number of row entries in the matrix and capital H denotes the number of column entries in the matrix, and Vk is the starting element of this matrix. Here, this capital Vk denotes the first column of this matrix, which is started by the vector small letter Vk, and capital Vk plus 1 is the second column, and so on. We can observe that the skew diagonal elements are the same. For example, we can observe that Vk plus 1 appear in this skew diagonal, and Vk plus 2 appears here, and so on. This particular structure of the Hankel matrix is useful in various system identification and signal processing tasks, as it captures the system's time and space dependent relations in a compact form. The Ho-Kalman algorithm was later extended by Kung using a singular value decomposition based factorization of the Hankel matrices, and this method is called as Ho-Kalman-Kung algorithm, which will be discussed in the rest of this lecture. Here, we will be using a discrete time unit pulse function as the input and can be defined as in equation number 4, where Uk equal to 1 for k equal to 0 and 0 for the rest of the time instance. Now, if we apply this pulse input to a linear system with a 0 initial state, we obtain the impulse response as in equation number 5, where y0 equal to c into x0, which will be equal to 0 since the initial state is 0, and y1 will be equal to c into x1, which is equal to ca x0 plus cb u0, and which will be equal to cb since x0 is 0 and u0 equal to 1. Similarly, y2 will be equal to cab since x0 equal to 0 u0 equal to 1 and u1 equal to 0. And in general, we obtain yk equal to c a raised to k minus 1 b. For the impulse response, the input and output data matrices can be represented as in equation number 6, which will be used next to define the Hankel matrix. Now, in the Ho-Kalman-Kung algorithm, the Hankel matrix is constructed using the impulse response data as in equation number 7. Here, the impulse response based Hankel matrix is factorized as a product of the extended observability matrix capital On and the extended controllability matrix capital CH. We obtain y1 as CB, which is equal to the first row of this matrix into first column of this matrix, and y2 is obtained as CAB, which will be equal to the first row of this matrix into second column of this matrix, and so on. Here, On and CH are called extended observability and controllability matrices since it contains capital N and capital H number of entries. And we assume this capital H and capital N are greater than or equal to the actual system order N. Here, if we know the true system order, then we can select capital N is equal to small letter n and capital H is equal to small letter n, which makes this as the observability matrix and this as the controllability matrix. And from here, we can see that the first row of this matrix will give the C matrix and the first column of this matrix will give the B matrix. And we can observe that the submatrix contains the first row till n-1th row of this matrix multiplied by A will be equal to the submatrix containing the second row of this matrix till the nth row. And by solving that equation, we can obtain the A matrix as well. However, in practice, the actual system order or the small letter n is considered to be unknown and we have to estimate it from the input-output data. In this lecture, we will be denoting an approximate model order by small letter s, which can be considered as an approximation or estimation of the actual order n. And to find small letter s, we can use the singular value decomposition of the Hankel matrix, which results in equation number 8. Since we assume capital H greater than or equal to capital N, we will obtain the SVD of the Hankel matrix H as shown here, where the matrix sigma is a square matrix containing the singular values sigma 1 till sigma n as its diagonal elements. And this 0 is a zero matrix of size n by h minus n. And it will be multiplied by VR in this right eigenvector matrix. Therefore, VR can be excluded and this product can be compactly written as W sigma V transpose, where sigma will be a square matrix and V will be an h by n matrix. Since sigma is a square matrix containing non-negative elements along its diagonal, we can write it like sigma raised to 1 by 2 into sigma raised to 1 by 2. And here we can also include an invertible matrix P, which is of size n by n. And in this lecture, we will be selecting P as the identity matrix of size n by n. This results in the factorization of the Hankel matrix as the product of On and CH as in equation 7, where this will be the extended observability matrix and this will be the extended controllability matrix. Note that the rank of the Hankel matrix is the number of non-zero singular values in the matrix sigma. And we have from linear algebra, the rank of the product of two matrices will be lesser than the individual ranks. For observable and controllable realization, the rank of On and CH should be equal to the small letter n or the actual system order. This indicates that the rank of H should be upper bounded by small letter n or the true system order. Therefore, to find an approximate model order S, we can find the number of non-zero singular values in the matrix sigma. We denote the identified model with the order S as in equation number 9, where AS, BS and CS are the identified system parameters. The approximate model order S can be computed as in equation number 10, where we introduce some tolerance epsilon to the singular values and identify the number of singular values in the sigma which are greater than or equal to epsilon. And by solving this equation, we obtain the value of S. So here we can have different possibilities. The approximate model order S can be equal to the actual order small letter n, in which case we have identified the exact order. And in some cases, the S can be greater than or equal to n when the data will contain large amount of noise and all. So in this case, we have an overfitting kind of model. In some cases, this S can be less than the actual order n. This can normally occurs when the system has some of the eigenvalues which are closer to 0 and has very faster transient dynamics. And this results in model order reduction, which means we can predict the output sufficiently accurate using a reduced order model. Once the approximate model order or S is determined, we can obtain a rank S approximation to the Hankel matrix H as in equation number 11, where sigma S and Ps are the S by S submatrices of sigma and P respectively, and Ws and Vs contains the first S columns of the matrix W and V respectively. So here this ONS and CHS can be considered as the observability and controllability matrix with the rank S. Earlier from the observability matrix equation, we can observe that the second row till nth row of this matrix will be equal to the first row till n minus 1th row multiplied by AS. Therefore, by left multiplying this equation with the inverse of this matrix, we obtain AS equal to this matrix inverse into this matrix. But here we have used the pseudo inverse since this is not a square matrix. For the observability matrix, we have the rows as C, CA, CA square and so on. And for controllability matrix, we have the columns as B, AB, A square B and so on. Therefore, BS will be the first column of the controllability matrix CHS and CS will be the first row of the observability matrix ONS. This algorithm 1 summarizes the Ho-Kalman-Kung based linear model predictive control, in which we first identify the system parameters AS, BS and CS, which is of an approximate order S. Then using these parameters, we can implement either output based or state based LMPC as discussed in the previous lecture. Next, we move on to a numerical example of Ho-Kalman-Kung based data-driven LMPC, in which the actual system parameters are chosen as in equation number 14. The input-output data is generated by a forward simulation of the linear system with these parameters with an impulse input of length 50. The value of the capital N and capital H are chosen as 5. And here the prediction horizon of the MPC is also denoted by capital N and which is also chosen as 5. The rest of the simulation parameters are chosen as in equation number 15. And in the MPC, a stabilization problem is considered in which the objective is to drive the system from a non-zero initial condition as here to the origin. Figure 1 shows the response of the Ho-Kalman-Kung algorithm based data-driven linear MPC, in which the plot A shows the pulse input, the impulse response in red color, and the response predicted by the identified model in green color. Figure B and C shows the response of the data-driven LMPC with the model parameters identified by the Ho-Kalman-Kung algorithm. Here we can see that the states are converging to origin, therefore the stabilization is achieved, and the control input satisfies the control constraints. The MATLAB code for the numerical example can be downloaded from the link given in the description. That leads us to the end of this lecture. Thanks for watching.